So today we're going to be talking about the design of nuclear reactors and get into a couple of the existing styles of nuclear reactors. This is 3 Mile Island right here. Oh, it's even a three-dimensional image of it. How amazing is that? So there are 2 reactors on this island. Actually, there's only one now that's operating, but there were 2. One of them operated for what, like a day before it had the meltdown. So the one that looks less clean, this is the one that has not turned on since the day it turned on, or shortly after the day it turned on. And then this has been operating continuously, I think. I think it's still open. If not open, it's only closed fairly recently. But that's 3 Mile Island. You can see these floating devices. Oh, you can actually see all the detail. That's pretty cool. How long does it normally take to build nuclear reactors? That depends on how many lawsuits there are filed to prevent the nuclear reactors from being built. If it's just a matter of you pour the concrete and start building something, it takes 5 to 10 years. If there's a whole bunch of lawsuits that get in the way that prevent you from making any progress, then you're looking at 10 to 15 years. The lawsuits and regulations are actually what drive up a lot of the cost of nuclear reactors today. So when people say it's really expensive by design of certain lobbying groups, rather than expensive if you just build the buildings. For example, there was a conversation I had with Robert Mueller, also on YouTube and on Rumble, where he basically said in South Korea they can build a nuclear reactor in half the time, or with half the money that it takes to build one in the United States. And it's all from regulation and Robert Mueller. It is Robert Mueller, isn't it? Maybe it's Richard Mueller. Hold on. I think it's Richard Mueller. I apologize, Richard Mueller. Richard Mueller. Richard A. Mueller. So, anyways, the interview that I had with him was about that, and that's where he went on there. Presumably there are only a handful of companies that can build them. That's true, and that's actually an issue because there are also only so many companies that can maintain them, and so if we continue to close them down without eventually the people who can operate them and stuff get more and more sparse, and the people who can build them get more and more sparse, and all of that technical capability is going to other countries that are actively building nuclear power plants. So let's see, presumably there are what happens, so I don't know which companies there are that do that. Thoughts on graphite tipped cooling rods? It depends on the nature of your system. And so thoughts on graphite tipped cooling rods for RMBK reactors is not very high. So it depends on what you mean by regulations, right? So Japan did turn off all of their nuclear plants, I believe, or certainly most of them, after Fukushima. They're starting to turn back on. The people in Japan, I just looked at this yesterday, I think. If you look at the public opinion of nuclear reactors in Japan, it has grown over the last decade as people kind of are able to assess what happened and what's happened since then, like what happened at Fukushima and what's happened since Fukushima, and are we making the right decision, and should we start ramping things back up? And so Japan is actually, I think, starting to get back into the game of that. The atomic bombs, as one of the things that we've talked about, and I'll bring up whenever the opportunity presents itself, is that with commercial nuclear reactors, you can't make a bomb. And so the regulation is mostly around nuclear waste and containment. We just had that thing about, or the last stream that we had was about nuclear waste. So do any nuclear plants use liquid nitrogen for cooling? No, you wouldn't want to use liquid nitrogen. So actually that's what we're going to be getting to today is the coolant on the inside. So let's go ahead and get started. And that way I can address this initial question. All right, let me pull up this drawing pad right here. And using this stylus right here, we will begin our discussion of nuclear plant design. There are 3 main issues that go into nuclear plant design that are, aside from the safety aspects, so just like the operations of the reactor. And those are, 1, you have to have the fuel. You have to have your nuclear fuel. All right, first time chat, thank you for coming. Hope things are going well for you. All right, you need to have fuel. The number 2 thing you need to have is a coolant. And the number 3 thing you need to have is the moderator. Okay, so this is for specifically a particular type of nuclear reactor or a genre of nuclear reactor that is called a thermal neutron, or a cold neutron. So a thermal neutron, a cold neutron, or a slow neutron, we call it a slow neutron reactor, as opposed to a fast nuclear reactor, which we won't get to today, but I will probably next time do a stream on fast nuclear reactors and how fast nuclear reactors are different than the slow nuclear reactors. So for a slow or a thermal nuclear reactor, you need these 3 things: fuel, coolant, and the moderator. And then of course you're going to have the safety systems, which is going to be the control rods, but that will be a separate aspect of this discussion. Okay, so your nuclear fuel is going to be the typical pellets that are about yay big, and it's got this uranium that's enriched in uranium-235 to roughly 5%. We'll call it 5%, although I believe that most commercial reactors are going slightly less than 5%, but 5% is still considered reactor grade. So it's 5% fuel, and then it's 95% not fuel, it's other uranium. So this is uranium-238, and this is uranium-235. 5% uranium-235 and 95% uranium-238. The uranium-238, it's just because, one, you don't want to enrich it all the way because then you run into nuclear weapons issues. And 2 is that you still do get some fission, it's a tiny amount, from uranium-238. And uranium-238 can absorb a neutron and turn into uranium-239. I'm sorry, can absorb a neutron, go through a series of decays, and then turn into plutonium-239. And that plutonium-239 is also a component of the nuclear fuel of the system. So uranium-235 is the primary fuel, but there's always other things that are going on when you have a bunch of neutrons flying around in this environment with big floppy nuclei, is that some fraction of them will either fission and contribute to the energy that is produced, so some fraction of the time you'll get those fission events, or you will get the uranium-238, you will convert it up into a fuel that's more readily spent, and that the most nearby one is plutonium-239. You can also get plutonium-241 and americium-241, but that takes additional absorptions that might not be readily available. Okay, so here is a question. Which ones are more efficient? Okay, I'm not totally sure what the question is related to, so we'll get to a variety of designs and we'll talk about the efficiencies. Okay, so you need to have a fuel. So you have these fuel rods, you have all these pellets. Those pellets will fit into, I guess, a fuel pin that's some length, and then several of those pins will be stacked into a fuel rod, and then those fuel rods will be put into an assembly that is lowered into the reactor vessel. The reactor vessel will be some kind of container that looks like this, and you have the fuel rods that are suspended inside that reactor vessel. Inside that, so the question is, which one is more efficient? The slow nuclear reactors, like the thermal neutron nuclear reactors or slow neutron nuclear reactors, those are the most efficient at absorbing the neutrons. However, there is energy that goes into the production of the fuel, the enrichment of the fuel, and so like which one in the end is efficient probably depends on a lot of things. But in terms, like the slow neutron reactors are more efficient at using the neutrons that are there because the neutron absorption cross-section or the fission cross-section is what, like 100 times larger than you get with the fast ones? Okay, so here are your fuel rods that are in here, and then you'll fill it with the moderator. So you fill it with the moderator. And you also have to worry about, let's try this one more time. For most reactors, you're going to fill it with a moderator, and that moderator is going to be water. For most reactors in the United States, and also most reactors in Asia, I think, are this way as well. Your moderator is going to be water, and that's because you get both oxygen that works as a decent moderator and hydrogen that works as a really good moderator. Okay, then you also have a coolant, and the coolant is what you circulate through the reactor core to remove heat from the reactor core. So let me redraw this over here. So here's your reactor core, like yay. You have your rods in here, and you want to circulate a coolant through here that you then drive your turbine with. So this is, I guess, the universal symbol for turbine. Looks like that. And then that's attached to a generator. And then you're going to cycle something through here so that so when someone says a coolant, that's actually the thing that produces the heat. It takes the heat from the reactor, pulls it out of the reactor, and drives the turbine with it, and then comes back in. So the coolant is actually the working fluid, or the working substance that drives the turbine. So there are your fuel rods, you have your moderator in here, and then you have your coolant that's also inside this vessel. Now, the most straightforward design for a light water reactor, the kinds that are, well, that we're going to be talking about right now, is one called a boiling water reactor. Boiling water reactor. And what that does is it uses, so here's your reactor core, and here's your fuel rods in it. And it uses the water that is the moderator as the coolant. And so it's this water gets pulled out, you drive the turbine here, that drives the generator, and then you cycle that water back down here. You have to condense it because it comes out as steam. So you have steam up here, and the steam gets pushed through the turbine to produce your electricity. You bring it down into this area, and then you have some kind of coolant or cooling area. So it's a condenser of some sort to take the steam and condense it back down to room temperature, and then you feed it back into the reactor. And so you're cycling the reactor through this system. Cold water comes in the bottom, it boils, produces the steam, and then that steam escapes and drives the turbine. So this is a boiling water reactor where you have one loop. So the coolant loop is also the moderator loop. So the moderator is pulled out of the reactor. The moderator slash coolant is pulled out of the reactor, drives the turbine, and gets put back in. So in this case, the water is both the coolant and the moderator. And there's one loop, which means, for example, if something were to happen here, like you spring a leak, so here's a leak coming out of here, that leak is going to be the water that was in the reactor core. And so if there's some contamination of that water from the reactor, then it's going to come out in the leak, and then this will be radioactive. So here's the radioactive. So that's going to be could be radioactive steam if something goes wrong. So you melt down, fuel comes down in here, you contaminate the water with radioactive material, and then that gets blasted out through some mechanism. So this is one of the issues that you confront with a boiling water reactor, is that the coolant and the moderator are the same fluid. That simplifies the design, but it also complicates the safety protocols. Now, how many boiling water reactors have actually spewed forth some kind of steam like this? The answer is 2, and it was basically hardly anything happened. Actually, it's 1, right? So 3 Mile Island essentially was this. Fukushima was not quite the same thing as this. Fukushima was a bit different. And Chernobyl wasn't this either, because Chernobyl had a different setup. So that's a boiling water reactor. For a pressurized water reactor, let me go back to this boiling water reactor briefly, because there's one important issue that we need to address. So here's the turbine, here's the generator, here is the loop of water, there's the condenser, and then it comes back in right here. The boiling water reactor is also under pressure. So you have pressure like this, like that Queen song. The reactor core is under pressure, and the reason is that water boils at 100 degrees Celsius, and it condenses, or it turns into a liquid at 0 degrees Celsius. So you only have a 100 degree window to produce to keep the water in a liquid form. So you have a 100 degree window to heat and cool the water. Now you are producing steam, so you have to get, the steam's also going to be at 100 degrees Celsius, but this is the most energy you can extract from it. The most energy you can extract from the steam is the heat capacity of water times the change in temperature. So the energy you get is the amount times the heat capacity of water times this change in temperature. And that change in temperature, the bigger that change in temperature, the more energy you can extract, and the more efficiently your reactor can operate. So the maximum efficiency you can get, we will use this weird Greek letter for efficiency. Well, that's not very good either. There we go. No, that's not very good either. Whatever. Okay, so the maximum efficiency that you can get with any heat engine is 1 minus the cold over the hot. Now this is and a steam cycle engine is not going to get this efficiency. This is a hypothetical efficiency or a theoretical efficiency that you get with a perfect system that's operating with a very specific cycle, the Carnot cycle. Steam engines don't operate with a Carnot cycle, they operate with a Rankine cycle, and that has a different efficiency. But that efficiency is always going to be less than this amount. And so this is a useful thing to get used to how, like what gain in efficiency do you get from one operating mode to another. Okay, so here, the best you can do is to, now these temperatures are measured in kelvins and not in Celsius. And so this would be, what, 373 divided by 273, which is like 1.5, something like that, or 1.3-ish. Oh, cold over hot, so it's 1 over 1.3, so these need to be switched. And it's 1 minus that. So 1 over 1.3 is going to be 0.7, so you get 1 minus 0.7, and you get a 30% efficiency, basically, is what you get from this. So that's if you're operating at the maximum separation between the cold and the hot reservoir. Usually these things are going to be operating, in some location. They're not going to be able to cool all the way down to freezing. They're going to cool down to the ambient environment at best. But typically they're going to cool down to whatever you can get it to within the time that the fluid is cycling through the condenser. Like however long it takes to cycle the fluid through the condenser, it will cool down by however much it cools down. And even whatever happens in the condenser, you've already lost, because this is energy that's being lost to the environment and not being put into the generation of the electricity. So it's actually the temperature difference that you get from going into the turbine to coming out of the turbine that matters in this calculation. Regardless, the moral of the story is, since you can't really change much what the cold temperature reservoir is going to be, the hot reservoir is easier to control. It's easier to raise the temperature of something. However, since water boils at 100 degrees Celsius, and if you're in a chamber that has both steam and water in it, then by definition it's at the boiling point, then you're limited in what T-hot can be. As a consequence, you pressurize this vessel. You allow the steam to build up in here to raise the pressure, and as you raise the pressure, you also raise the boiling point. So the boiling point now goes from 100 degrees Celsius up to I think it's like 250 is a pretty typical, so around, between 200 and 300 degrees Celsius is about the best you can do. This might be something that we look up, but you raise this temperature, and now that improves your efficiency because the steam has more energy in it, and so you're able to extract more energy from that steam. This 250 degrees, I think the pressure is several atmospheres, 6 or 7 atmospheres. It's not 100 atmospheres, but it's multiple atmospheres. But that does raise this boiling point and therefore gives you a larger temperature range where you can extract the heat over that temperature range. And that improves your efficiency up to about 30%. Okay, so why does it have to operate at the saturation temperature? In this case, it has to operate at the saturation temperature because the moderator, the fluid, and the steam that drives the engine are the same fluid. So the water and the steam come from the same, what do you want to call it? What's the right word for it? They come from the same, airplane flies overhead, reservoir. So it's the same reservoir of water that is the moderator and that produces the steam. The next design that we'll talk about, there's a difference in it, and those are the ones that are most used in the United States of America, especially for more recent reactors. Okay, so what does this mean? Well, because this is under pressure, then you have to worry about what happens. You have a pressure vessel, and pressure vessels can fail under certain circumstances, and so you have to design your building so that pressure vessel doesn't, if that pressure vessel does fail, that you can contain the material that would come out. Because if all of a sudden this pressure vessel were to rupture, then it would drop from, let's say 5 atmospheres. It would drop from 5 atmospheres to 1 atmosphere. That would mean that you have a liquid in there at ambient pressure that's at 250 degrees Celsius, and so it would immediately turn into steam, and as a consequence it would immediately increase its volume by a factor of 100 or whatever it is, maybe 1,000, so that now you have all of this steam that's trying to fill up space, and that steam could carry with it whatever substances may have leaked out that you didn't want leaked out. For the most part, the control rods are operating in good order. If you take into account like all the numbers of years that nuclear plants operate without incident, it's huge numbers. So they're the safest plants that we have there out in the world. And it's because the safety events or like safety concerns are so rare, they become gigantic international news. All right, so this is a boiling water reactor. Let's adjust this slightly and get a pressurized water reactor, and this is more common in the United States. Pressurized water reactor, especially with more recently designed reactors. Pressurized water reactor looks like this. You have the same reactor core, you have the same fuel rods, you have the same water moderator. However, you have a separate reservoir of water out here, and this reservoir of water comes into this, into the reactor core, is piped in, goes through a heat exchanger, so it's just in contact with the water that's inside the reactor core. It absorbs energy from that reactor core and then is piped back out. So this loop of water, so that's where you get the steam. So now this is steam, and you drive that over here. Here's your turbine. You drive the turbine, which drives the generator, and then you bring it back in, and you have this outside loop. So this outside loop here, the water in this loop does not come in contact with the water that's used as the moderator. So now you have a separate moderator and coolant, even though it's the same fluid. They're both water, but one of them is only a moderator, and the outside loop is only the coolant. So in comes this thing. It picks up energy from the reactor core and then is driven back out here, drives the turbine, comes back in. You also have to condense it and do all that kind of stuff. But this secondary loop, it increases the complexity of the design, because now you have to make sure that everything is sealed up nicely as it transitions into the reactor core and back out. So it does complicate the design, but it makes it safer. The reason it makes it safer is because this thing, you're not taking any of the moderator out of the reactor core. So if something happens in the reactor core, it doesn't get into the loop that drives the steam engine, and therefore it doesn't come in contact with the atmosphere. So with a boiling water reactor, if there is some rupture in the system, it exposes the environment to whatever happens to be in the reactor core, which again, for the most part, is nothing except for fuel rods and control rods. But in the event that something catastrophic happens, with a pressurized water reactor like this is a pressurized water reactor, that the stuff that's in the reactor core doesn't have a mechanism to get out of the reactor core. Okay, another thing that pressurized water reactors do is that it allows you to operate at even higher temperatures. So you can raise the temperature inside the pressurized water reactor higher, because you don't have to worry about the fact that there's a phase transition going on inside the reactor core. It's all fluid in the reactor core. You're sending in this. If this turns into a gas, that's fine. That's what you want to drive the turbine. But you don't have a reservoir of steam. You don't have a reservoir of gas up in the top of the reactor core like what you get with a boiling water reactor. So that second loop is the more common design, certainly today in the United States, to have it like this. So water comes in, comes out. Otherwise, it's the same design. Okay. These are light water reactors. These are the special kind of, like the typical things that operate in mostly in the United States, around the Pacific Rim. And then there's a different type that we'll talk about that's more related to what was going on in Chernobyl. So the Chernobyl reactor was not this type. So we'll go back to the elements that we need. We need to have fuel. So we have fuel. In this case, we're going to use the same fuel. We need to have a coolant. Okay, we'll use the same coolant, so we're still going to use water circulating in there. And then the last thing that was different in the design from the Soviet I think it's RMBK model, is the moderator. Okay, so it has a moderator, which means it is still a slow neutron reactor or a thermal reactor, but the moderator that they use here was carbon. So graphite moderator. And here was their design. Reactor core, you have fuel rods in here. They have the moderator was surrounding the fuel rods. They had like a graphite structure, then the fuel rods were inserted into the graphite structure. And it was that graphite that slowed down the neutrons so that they could be more readily absorbed. So you still have the water flowing through as the coolant, separate from the moderator. In this case, the moderator is a solid instead of a fluid. and there you go. That was the system. So again, this is going to be pressurized because you want the water coming through here, you want to come out at high temperatures, and so you have to pressurize it in order to get it up to the high temperatures, and then that will drive your steam turbine. This was the design from the Russians. There are some nuclear plants in the United Kingdom that operate with a graphite moderated. You can also use a gas cooled, so the coolant, so far all the coolant that we've seen is water. But you can moderate, or you can cool the reactor with gas. You can have a gas cooled reactor where you're cycling gas through the reactor. An advantage of using a gas coolant instead of a liquid coolant is that gases have already gone through the phase transition. So it's the phase transitions that really mess up the system, because that's where you get a big change in the properties of the substance that you're working with. So if all of a sudden things freeze, then you have a problem, as we saw in Texas. You also have an issue where if something boils, and in particular if something boils, so you have your fluid in there, and if the fluid boils, it's trying to turn into a gas, which is going to take up more volume, and that's going to increase the pressure inside your container, and it might exceed the safety conditions or like the pressure tolerances of your vessel. So going through a phase transition is the thing that needs to be avoided. And so an advantage of going with a gas for the coolant is that the gas is already in the gaseous state, and the next phase transition doesn't happen for a long time. So with water, the phase transition is like 100 Celsius. If you pressurize the water, you might get the phase transition to like, it's not quite 300 Celsius, but let's say we'll take 250 Celsius. So that's a C, 250 Celsius. So you can operate up to here, at which point you'll go through the phase transition, and then bad things are going to happen. For the case of a gas, if you want to, when does the gas go to the next phase transition? When does it turn into a plasma? The answer is like 7,000 Kelvin, okay, or at least 3,000 Kelvin. That's like the temperature of a star, of a low mass star. This is like closer to the temperature of the sun. 6,000 Kelvin is the temperature of the sun. And so that's a really high temperature to get a plasma, and everything would melt before you got there. And so you have a lot more latitude with a gas. You don't have to worry about the gas going through some phase transition and as a consequence breaking your reactor core apart. Okay, so there are a couple questions. Let me answer these questions really quickly. These are not weapons grade. Not weapons grade fuel, because the weapons grade fuel is enriched in uranium-235 up to 80 to 90%, usually 90% or higher. Where the stuff that's used in a reactor core is only 5%. So none of this stuff, you can't make a bomb out of it. You cannot reach critical mass with stuff that's enriched as poorly as commercial grade reactor fuel. There's no critical mass because there's no way to get the density high enough. You can only reach critical mass once the density of the uranium-235 has gotten sufficiently high, which means it has to be enriched up to that point, and then you can get a critical mass. All right, let's see. How different, we will talk about the containment, and we'll talk about that momentarily when we do the safety stuff, assuming that I have time for the safety stuff, which I think I will. Certainly I'll have time for the control rod stuff. How different would a modern reactor be in the US, because it's been 50 years since the US last made a nuclear power plant. So the most recent nuclear power plant, I think there's one that's almost finished in is it Georgia that's almost finished, or South Carolina? So a modern reactor, okay. So how do modern reactors affect this design? That's actually something that I'm going to address probably next time. I don't think I'll have time to get into it today, but I'll just give you a primer about what's going on. So either today, probably not today, but next time we'll talk about the different failure modes, how these things fail. And in particular, one of the things that fails here is that you have to actively control the system. And we'll get into the control in a minute. And the modern reactors are ones where if you cease controlling the reactor, then the reactor puts itself into a safe state. Where the older generation of reactors, so all the reactors that we've discussed here, the designs that are operating for the most part around the world are generation 2 nuclear reactors, which are reactors that were designed in the 1950s and 60s and built in the 60s, 70s, and 80s. Anything that we would build today would be a generation 3 or a generation 3 plus reactor, which is basically generation 2. We have 50 years of experience or 40 years of experience putting these things together, watching how things fail. Like here's something that's failing, we'll turn the reactor off and then we're going to fix it, and now we've learned something. And so the modern reactors they don't rely on external systems to put them into a safe state. Where the Generation 2 reactors, you have to have a bunch of controls. It's like you have something balancing, the reactor's balancing, and you have to keep it balanced. And so if power gets cut off or something like that, then you have to actively cool the system. You have to run batteries and backup generators and things like that. Where with the Generation 3 reactors, they're designed specifically so that if power to the system fails, then the reactor puts it into a state where it can be left alone for a period of time before you actually go in and start messing around with things. So it's not like a rush to keep it safe. It automatically goes into a safe mode, and then you can approach it at your leisure once you've assessed, okay, what's going on and how do we address this thing? One of the issues to consider when you're looking at these reactor problems, the safety issues that have come up over the last 50 years, like three safety issues in the last, three big safety issues in the last 80s, since the 1970s, right? So that's 50 years. I can't remember what I was going to say other than because I kept trying to come up with this. Oh, they were all three of those reactors are the Generation 2 nuclear reactors. There's never been an issue like that with a Generation 3 nuclear reactor. Okay, so that was that question. A modern reactor is different. It's a new generation where a number of other safety protocols have been put in place, and so I will go into more detail into those kinds of things. Probably not on this stream, but on a future stream. Can't you use a separate coolant system in a boiling reactor? Well, if you use a separate coolant system in a boiling reactor, then it's no longer a boiling reactor. So that the fact that it uses the same thing as the moderator, that is also the coolant, is the characteristic property of a boiling water reactor. Okay, difference between a gas state and a plasma state. The difference between a gas state and a plasma state is that the gas has the electrons attached to the nuclei. So you have, a hydrogen gas or hydrogen atom with the electron around it, and a plasma, the electrons are no longer bound to the proton. So it's still electrically neutral. If you take a volume of it, it's still electrically neutral, but the atoms are no longer, it's not neutral atoms. The electrons have been stripped off of the atoms, and so you have a sea of electrons and a sea of nuclei, like protons, that are coexisting in some volume. The charges have been separated, and so that's what a plasma is. And that can cause problems. The main issue with a plasma is that everything is melted by the time you get to those temperatures. So if you're talking about 7,000 Kelvin, and you just released 7,000 Kelvin gas or plasma in a stainless steel container, the steel would melt, because it melts it. The steel probably melts at 2,000 Kelvin, something like that. So you got a long ways to go before there's that phase transition. Okay. Active versus passive safety is the difference between Generation 2 and Generation 3. Okay. Plant Voigtla in Georgia, South Carolina border, but it's correct. Supply issues and construction delays have pushed back the start of number 3 until next year, probably fall or winter. Plant 4 might be online in 2024. 1 and 2 are currently running. Thank you for that information. Are all the computer systems in nuclear power plants cut off from the internet? That I don't know. I do know that my understanding is that the majority of nuclear power plants actually have separate control rooms. They have 2 separate control rooms. They've got the real control room and they've got a mock control room. And that periodically, as in relatively frequently, they will have a crew in the mock control room, and then they'll run through disaster scenarios where different lights go blinking off, and then how do you address this when these come up? Because nuclear reactor failures are so rare, you don't get any practice. You can go for a whole generation without any practice, like real world practice, and so you have to train for them constantly. Is there any answer of what to do with the waste from any generation plant? So Geyser, that's a great question. And when I talk about, especially when I talk about the next generation plant, the 4th generation of plant, that will actually change a lot about how you deal with nuclear waste. For the moment, I'm going to point you to my previous video. It's on YouTube and Rumble, and probably still in the VODs here, where I did an hour on the nuclear waste and what the nuclear waste is. I will also plan to do a stream on what are the storage options for nuclear waste long term. But that, for the most part, won't be today. I will say that there is one of the things that's being done for nuclear waste right now is there's a company out of Berkeley, California called Deep Isolation. And Deep Isolation is they drill down way down, like a kilometer down, which is lower than Yucca Mountain. It's lower than the water table by a long shot, right? The water table is up near the surface, and so otherwise you wouldn't be able to dig a well to it. So there's like dirt, and then the water table, which is tens of feet below the surface, and then you're basically at bedrock till you hit the core. And so this deep isolation, they go down about a kilometer, and then they use horizontal drilling that's been developed over the last couple decades to drill out another kilometer, and then they just take these spent nuclear fuel containers and put them a kilometer underground or a mile underground, at which point they're way safer. I mean, like nothing happens at that depth in the crust. Okay, so that's those are some of the options. We'll go into more detail about those things, but to give you a filler for what's happening. Generation 4 nuclear power plants have a different waste stream, and so that's something we'll revisit. Firewall between digital controls and analog controls, I read. Okay, that sounds plausible. Better question may be, do the computer systems in nuclear plants have USB docks? I doubt it. We made containers that would get filled with boron cement. Yeah, so there are a number of different ways that people handle the nuclear waste, and so that will be a stream in its own right. Let's see. Are there water chairs and water sofas too? In order to get water sofas, those are a bit more expensive. Water beds are a bit cheaper than water tables. But anyway, so earthquakes. So now the issue with earthquakes is, what is the concern with earthquakes? The concern with earthquakes is that you open something up and it's exposed to the water table. But if you're already below the water table, then an earthquake won't be able to do anything. It might crack the containers, but then the question is, how does the radioactive material distribute through bedrock? And the answer is extremely slowly. Okay, so let's keep going with where we were. We have the fuel, the coolant, and the moderator. We've already talked about the boiling water reactor. We talked about the pressurized water reactor. We talked about this graphite-cooled reactor. Graphite moderated reactor that uses both. It could use water as the coolant, or it could use gas as the coolant. I read that there is a gas-cooled, or at least one gas-cooled reactor that's being used in the United Kingdom. And so, so there's that. Now we need to talk about, how do you control the reactor once it's going? How do you turn it off? Okay, so the way that you turn a reactor off. Okay, so here's a comment. I heard somewhere that there is some type of bacteria that eats nuclear waste. I don't doubt that there might be a bacteria that eats nuclear waste, but that wouldn't change the radioactivity of the waste. The reason is that when you look at an atom, so here's an atom, here's the nucleus, this is what's going to decay, right? Excuse me, you're going to have some beta emission coming off of the nucleus. The electrons are way out here. And so anything that deals with the metabolism of some bacteria is going to be dealing with the electrons that are out on the perimeter. And so, and that's, you know, if this is 1 meter, which is not 1 meter, but let's pretend that it's 1 meter, this is 100 kilometers distance. So anything that's chemistry, so that would be any biological thing, would be way out here, and it wouldn't affect the radioactivity of the core. So even if there was something that could eat the uranium or the plutonium, it would not it wouldn't change the radioactivity properties of it. Okay, let us talk about how you control the reactor. So inside this reactor core, you have, looking down from the top, you have a series of fuel rods like this. They're arranged in some configuration that's really special, that someone has calculated to maximize the efficient use of because you want to have the control rods to be close together. You want to have the fuel rods to be close together so that the neutrons that come out of one fuel rod will impact the material in a different fuel rod and then create a fission and then also send everything back in. You also want to have it compacted. You want to have a minimum amount of surface area. And so typically you'll see reactors where the fuel rods are put in an assembly that is roughly circular, because a circular assembly is going to have the smallest perimeter and for the amount of material that you have on the inside. The fuel rods do have to be spread apart, because if they're not spread apart, between the neutron leaving one fuel rod and coming and entering a different fuel rod, this is the distance over which you have to slow the neutron down. So you have to have several neutron bounces to slow it down, to bring it down to the temperature of the coolant, or I'm sorry, the temperature of the moderator, before it enters the other fuel rod and then creates another fission. So you can't get them too close together, or else all the neutrons will be fast. You haven't had the chance to moderate them. But if you get them too far apart, so suppose that all your fuel rods are too far apart, like this, then you have a neutron that comes out here. Yeah, it slows down, but then there's nothing for it to hit, right? The available material is so sparse that your reaction rate goes down. So you want to concentrate them down to the point where everything, you can optimize this. If it's too close together, then so there's going to be a spacing. So if we go space like this, and we look at the rate, like the reaction, there's going to be something that looks like this. If the spacing is too close, you turn the reaction off because the neutrons aren't moderated. And if the spacing is too big, then the reaction turns off because you don't actually cause another fission. The uranium-235 nuclei are too far apart. And so there's going to be some optimum spacing for your reactor fuel rods. Okay, so here is your fuel rod configuration, and you need to have a way to shut this down. The way to shut it down is to turn off the supply of neutrons, because it's the neutrons that initiate the fission, and so it's going to be, the neutron is going to be the source that you can use to eliminate the fission. So inside, or interleaved among these fuel rods, are a set of control rods. So you'll insert control rods into here. You'll either insert them or retract them inside this array. And the control rods are neutron absorbers. So something that has a good fission cross-section would be like uranium-235 or plutonium-239 or whatever. So these are the kinds of things that are going to be good nuclear fuels. What goes in your control rod is going to be some lighter element that is readily absorbs neutrons, like wants to absorb neutrons, because it will put it into a more stable configuration of the nucleons in the nucleus. So you'll put like a neutron poison in it, something that absorbs neutrons and remains stable once it absorbs the neutron. So you don't want to have these be radioactive. You want them to absorb a neutron and then be happy with where they are. So this could be, I don't know what's in the control rods. Let's make something up. So it's control rhodium. So control rhodium, this is probably something we should look up online. What is in the control rods of a nuclear reactor? So there's a question about a hexagon shape, and the hexagon shape, if you had a hexagon shape for this, that's approximating a circle, right? It's a reasonably good approximation to a circle. A square, if you had a square of control rods, like your whole reactor design was square or rectangular, then the corners aren't going to contribute very much because they don't have much viewing angle to the rest of the fuel rods. And I meant to say fuel rods for that whole last thing. So if your fuel rods are in a rectangular configuration, then the corners of that are not going to have a lot of places where their neutrons are going to be able to continue and perpetuate the reaction. And so a hexagon is approximately circular. It's certainly more circular than a square is. Okay, let's see. What is this thing? Control rods control the rate of fission of the nuclear fuel. Their composition includes chemical elements such as boron, cadmium, silver, hafnium, or indium that are capable of absorbing many neutrons without themselves fissioning. Oh, and this is interesting. Capable of absorbing many neutrons without themselves fissioning. So that, there you go. I'm surprised that boron made that list. That seems a little weird, but okay, fair enough. Hafnium, additional means of reactivity regulation, so there you go. And that is what these control rods do. So you have this hafnium or whatever boron control rods, and then you lower them into the reactor core or pull them back out of the reactor core. You can also raise them up. It depends on the design. But since gravity points down, it's usually easier to lower them down in, because the water, like your working fluid, is going to be at the bottom of the reactor, or your moderator is going to be at the bottom of the reactor. Do the control rods expire? They probably do expire. In general, you don't use them that much. You use them very little when the reactor is going. So if you were to plot over time, like where does electricity come from over time? So you have, here is your electricity consumption, and here's your time. And you'd have like okay, solar is going to go like this, and wind is going to go like this, and you're going to have coal that's going to flop around, and nuclear is going to be like that. So when you turn a nuclear plant on, you let it run. It does its thing. It operates in terms of its throughput, like in terms of its, what do they call it, the capacity factor? What fraction of the time is it actually operating? Nuclear is like above more than 90% of the time online. Solar, it's like 25 or 30% of the time, where solar is actually online. Wind is about the same. Coal can be turned on and, well, okay, so coal can't be turned on and off just directly, but it's going to operate probably around like 70, and then you'll have natural gas that fills in all the gaps. But nuclear power plants, you turn them on and they just run. And they run, like you're using it, you might as well run full bore, and so they just operate at the maximum, or close to, like they operate at some kind of optimum operating conditions. That will generally be with the control rods, not in the system. Okay, so let's take a look at, here is your reactor core. Here is your fuel rod. We'll put in 3 fuel rods like this, and then you'll have a series of control rods up here that you can lower in between the fuel rods. That way, you have a neutron that comes out of the fuel rod from the fission, and that neutron will be absorbed in the control rod and is no longer able to cause a successive generation of fission events to take place. So these control rods those are the important things in terms of how do you shut the reactor off. So if the reactor gets too hot, then you lower the control rods in, that shuts down the reaction, and everything will start to cool off. If you need to ramp it back up, then you pull the control rods back out. You can't shut the reactor off completely and then just start it back up again, because this is a detail that we're going to get into in terms of what's actually going on in the nuclear processes. We won't do it this time, but on a future stream, we'll talk about, as the fuel is being spent, there's a whole bunch of stuff that's being built up inside of it. And so that limits, if you turn a nuclear reactor off, it limits your ability to turn it back on until some of those things have been addressed. Some of those nuclear processes have done their thing. All right, let's see. Do control rods expire? I think I answered that, but I'll answer it again. I suspect that they probably do expire over time, but not as fast as the fuel rods. The fuel rods, a typical fuel rod will last like 5 years or so. And so you'll refuel the core, have it operate. I believe that they typically will remove a few rods at a time. So when you're going into service the nuclear core, you will open up the top and you'll pull out certain rods and insert other ones in their stead, and then replace it. And then like a month later, since you're talking about a 90% capacity factor, maybe it means that you shut it down for a couple weeks every 6 months or something like that. That seems like a bit much. But anyways, you shut it down once a year, open the top, pull out some fuel rods, put some new ones in place. And you don't want to replace all of them at once, because you want to have the right mixture of total nuclear fuel. If you replace everything at once, then you're going to start with 3% enrichment, and the whole efficiency of the system is going to decline over time. So your throughput is going to decline, and that's going to make your nuclear power contribution to the electric grid fluctuate from one day to the next. So instead what you'll do, say you have 500 fuel rods, every year you'll replace 100 of them. And then the next year you replace a different 100, and the next year you'll replace a different 100. And that way there's always kind of a consistent mixture of fuel in the system. How long in length are the rods? So the rods are typical, like the length is fairly standard. It's probably a couple meters. I believe that the RMBK reactor, the one that went off in Chernobyl, the control rods were like 7 meters, so they're really long. So coal, etc., are usually used where there's a spike in energy need, like in the winter. So natural gas is the easiest thing to turn on. Coal is moderately easy, takes a few hours to ramp up a coal plant. For a nuclear plant, if you're starting from scratch, it doesn't take that long to ramp up. But if you turn it off and then you want to turn it back on again, you have to wait. So this is how you control the rate of the reaction taking place. If it's going too fast, you drop the control rods down, it absorbs some of the neutrons, slows the reactor down. If you need to ramp the heat back up, then you raise it back up again. So suppose, for example, you have some load on your system. So here's your power plant. Looks like this. You have your cooling towers. I guess that's something that I should mention. in the design, but I'll come back to it. So here's your cooling tower. It doesn't look like that. A cooling tower, well, I guess it looks kind of like, oh man, it's exactly the same thing. Here's your cooling tower. It looks like this. Okay, and here's your power plant. And so if here's a house and they turn on all the lights in the house all of a sudden, so here's all the lights shining brightly, and you have your power cables that go over there. And so that's going to put a load on your power line. And as a consequence, that load is going to cause the turbine to turn more slowly, because you're forcing the turbine to supply more energy to the power lines, to the grid. And that, as a consequence, it's going to slow down. It takes effort to do that. And so at that point, you want to ramp up the temperature so that you can deliver more energy into the turbine, and that would be where you can use the control rods to kind of match the demand in real time. The way that this is measured is that it's how close to being in sync is your turbine compared to all the other turbines that are connected together on the electric grid, because they all have to be running in phase with each other. Okay, let's see. These cooling towers, when you look at a nuclear reactor, the cooling tower, that is where you're taking the water that came out of the system. So it's gone through the turbine, and you need to cool it back down in order to put it back in and heat it back up again. So you cool it down by putting it in these cooling towers, and that allows them to come to a lower temperature where you then feed it back into the reactor core. So that's what these towers do. Now, inside the reactor itself, because most reactor cores are under high pressure, like either the boiling water reactor or the pressurized water reactor, all these things are operating under high pressure. In fact, I can't think of a nuclear reactor that doesn't operate under high pressure, at least right now. So because it's under high pressure, you need to have a building to protect the environment in case this thing ruptures and all of that gas leaks out. So here's the thing rupturing, here's all the gas leaking out. You need to have a building that contains your reactor core, and this is called the containment building. So the containment building, that's the business end that's where the reactor core is located. So let's take a look back at this image that we have pulled up here. This is 3 Mile Island. So these are the cooling towers. This is the containment building right there. So can I zoom in further? Yes, I can zoom in further. This is the containment building. This is the containment building to the other side that got turned off, like the meltdown happened here in 1978 or something like that. So this one has basically only ran for a few months. This has been running, or at least ran for many decades. And this is where the reactor core is located, is in that containment building. If I go to a different nuclear reactor, so let me go to a different nuclear reactor. This one's in Pennsylvania. So I'm gonna switch layers so that I can scroll a little bit faster. So we'll come out of Pennsylvania and we will move from here over to Arizona. So we come across the United States of America over to Arizona. Outside of Phoenix, that's Texas. Here's New Mexico. Arizona, Phoenix. Over here is the Palo Verde nuclear plant. So this is the Palo Verde nuclear plant. I will zoom in on it. That's the entrance to it. This is the nuclear plant itself. This one has 3 reactor cores. And you can see, again, this one doesn't have the three-dimensional view, but these are the cooling towers, cooling ponds, or whatever. And the reactor vessels themselves, the containment buildings, are these ones. So there's a containment building, this is a containment building, this is a containment building. These are all just under 1.5 gigawatts apiece. I think they're 1.3 gigawatts apiece. And so this whole system, this nuclear plant is going to have 4 gigawatts of power total. So that's pretty cool. Here, if we go to Diablo Canyon, so Diablo Canyon is in the news a lot lately in California. It's on the shore, dimly seen through the mists of the deep. I think it's up here somewhere. Let's take a look. Diablo Canyon. Okay, Diablo Canyon again. This one has 2 reactors, and you can see those 2 containment buildings right there. Now these containment buildings they're pretty gnarly. These things are so strong, you could take an airplane, you fly an airplane into the containment building, and the airplane disintegrates. You smash a car into the containment building and the car crumples, and the containment building just sits there and brushes it off and keeps doing what it needs to do. These are like 3-foot thick concrete walls on all sides. It's a lot of concrete. It's like building a dam, except it's around this containment vessel. Okay, let's see some more questions. Giant nuclear. What I heard, ship subreactors are sealed out entirely rather than refueled. Have a record of being the safest reactors in use. Okay, so I don't know if what the current type of reactors are used, like how they're integrated into the system. I believe that the current reactors for the modern nuclear submarines, and the reason you want a nuclear submarine, if you're a naval power, you want a nuclear submarine because then you don't have to surface. So subs are most vulnerable when they're at the surface. And if you have a diesel-powered submarine, then when you have to be on the surface in order to run the diesel engines. And so you'd come up to the surface, you would run your diesel engines to charge your batteries, and then you would submerge, and then you'd run off battery power. So that's the problem. Either you have that or you have a snorkel. So you run a snorkel up to the surface so that you can get air down to your diesel engines. And so with a nuclear-powered submarine, you don't need the diesel engines anymore. And so you have a nuclear core, and then you leave, you submerge, you leave port, you submerge, you stay submerged for 3 months at a time, 6 months at a time, and then you come back, and you only have to submerge, or you don't have to re-emerge from underwater so that the crew can get off. If we had robot crew that didn't have to, suffer any deleterious effects from being in a can under the ocean for 5 or 6 years, then they would just stay underwater the whole time. My understanding is, I could be wrong about this, but I believe that the current nuclear submarines, the reactor core is designed so that it will operate continuously for the life of the submarine, and then they just decommission the whole submarine all at once. The previous versions of nuclear submarines, they would bring the ship up to the surface, cut a hole in the top, remove the whole reactor core, and then store the reactor core and replace the whole reactor core, seal everything back up, and then send it on its way. I don't think that the most recent iterations of the nuclear submarines work that way. What they did was they would take those nuclear cores and then they would store them up in Washington State at the, what's it called? It's where LIGO is located, the Hanford nuclear site, outside of the Tri-Cities area in Washington State. And so here's Diablo Canyon. These are the 2 containment buildings that are there. What was I going to... I think there's a video. I want to see if there's a video. Hopefully we can find it really quickly. If we can't find it really quickly, then we'll just punt on it. But like a video of smashing into nuclear containment building. Okay, crashing a 100-mile-an-hour train into a nuclear fuel container. So this is a container. This isn't the actual containment building. We'll see what happens.
Plowed headlong into the derailed flask and wagon.
So here comes your train. It's going to be amazing. Now, okay, so this is actually smashing it into the stuff that they store the nuclear waste.
"32 different cameras captured the scene from many different angles."
So that's what they're storing it in. And there's the train smashing into it.
There was even a camera on the front of the engine. But whichever way you looked at it, it was a tremendous test of the strength of the fuel flask.
And in the end, the train was gone.
Drawn hook on the front of the locomotive hit the edge of the flask, but the lid stayed bolted in position. There was some scarring of the steel and buckling of the outside cooling fins. But
so that's what... There's other ones where they smashed airplanes into it. Anyway, so these things are pretty robust against almost anything you can throw at them. Okay, so those are the... Oh, let's take a look at Fukushima. So Fukushima also had a containment building. So we'll scroll out. That is California. Fukushima is in Japan. So we'll come over to Japan. It's going to be amazing as we scroll into the... Wow, the Phoenix. There we go. Fukushima's up here. And let's find it. Fukushima. Okay, so it's got to be, it's Daiichi, I think, is the Fukushima Daiichi. There we go. So this is the Fukushima nuclear power station. It's near the ocean because you need to have a water supply to cool everything. There are, I believe, 6 reactor cores at Fukushima. It looks like they're doing quite a bit of construction, reconstruction. This reconstruction is because of the tsunami, not because of the nuclear power station. The tsunami wiped, like there were 20,000 people that died from the tsunami. There was maybe 1 that died from the reactor core. So there were 2 reactor cores. It looks like they are gone now. I thought that there were 2 reactor cores over here. But either way, these buildings, there were 4 reactors right here. My understanding is that there were 6 total. And these are not the containment buildings themselves. The containment buildings are actually inside of these structures. So if we look at a cross-section of the Fukushima reactor design, this is what the buildings look like on the inside. Where is it? Okay, here we go. Okay, so this is those rectangular buildings that you see is this structure, and the containment building is actually inside those buildings. So the containment building is this piece of monstrosity, which is just a bunch of cement, right? It's a bunch of concrete poured around it, and then there's the reactor core in the center. In this case, it looks like they insert the control rods from underneath, but there's the reactor core. You take this lid off. Here's the crane that would come in that would remove the fuel rods. So pull the fuel out. You put it in these containment vessels over here. We talked about this last time, that you put them in there because once you pull the reactor core out, like the fuel rods out, they're still radioactive, and so they still give off a lot of energy, and so you still need to keep them cool in order to dissipate that energy. And so this pool of water up here is to help dissipate the energy from these spent fuel rods. So there's the fuel rod. So if you want to refuel this plant, you lift off this lid, you unscrew the top of the reactor core, you use this crane to pull the fuel rods out, deposit them in this nearby cooling tank, take the new fuel rods, stick them back in, tighten this on top. It looks like there's a second layer that you put on top of that, and then you put the concrete lid back on, the cement lid back on. And so this cement lid is part of the containment building, and that's this. All of this structure out here, that's just an overall protection to the whole building itself, so that the workers can work without getting rained on. I will point out one of the important things in the design of Fukushima is this upper floor. So when you look at the upper floor, you'll notice that these walls are solid, and then these walls are not solid. There's a skeleton, basically, and then a skin, a fairly thin skin of blast panels in the top, so that if there is some kind of explosion, the whole upper portion of the building is supposed to fly off. And so when you see pictures of the Fukushima disaster, here's an oblique view. You can see the main building is cement, the the containment building is even thicker cement, and then this top floor is basically just sheet metal walls with some framing. So if we look at the Fukushima disaster after, I don't want to do aftermath, I want to actually see the images. None of these are quite, okay, let's take a look at this one. So this is when they're demolishing it, so that's not really it either. But if you look at the pictures right after the event happened, you'll notice that it's the top floor that is blown off. So like here, it's the top floor that blew off, and that's how it was designed. It was designed to fail that way. Okay, that's a natural gas plant, I think, so. All right, anyways, so when you see those pictures, you'll see the top of the buildings. I think there were 2 buildings in particular where the top blew off, and that's because they functioned as they were designed to function. Okay, let's see what other questions I have come up. If you lower the control rods and power output does not go down. Okay, now, so let's talk briefly about the control rods in Chernobyl, because that's different than what was going on. 2 main design differences with Chernobyl, the RMBK reactor, compared to the reactors that we use everywhere else on the planet. So the first and most important issue is this was the RMBK reactor core. It was a slightly different shape. It wasn't a cylinder like these other ones, or it wasn't a tall cylinder like these other ones. So here's the reactor core shape. Looks like this. And now I'm going to draw the containment building. Okay, I finished. So there was no, you may have noticed that I didn't draw anything. There was no containment building to the RMBK reactor, the Chernobyl reactor. No containment building. All there was like a warehouse, like a skin around it. There was no concrete structure that surrounded this in case of a meltdown and a release of a whole bunch of steam that would then only impact the containment building. All designs in the United States, all designs everywhere else, use a containment building except for in the old Soviet Union. So there was no containment building, which means that if anything gets out, there's nothing to prevent the stuff from leaking into the environment. There was a warehouse around it, so it was like inside of a building, but it wasn't a containment building. It wasn't thick, safety, concrete structure. So that was number one problem. Number two problem was the control rods. So here is your reactor. Here are your elements. Remember that you have graphite moderated. So here's graphite in here moderating everything. And the control rods for the Chernobyl plant looked like this. And the control rods for the Chernobyl plant, the bottom of that, this right here, that was also graphite, so carbon. And what had happened there was they were shutting down the reactor. They were like, okay, never mind, we don't want to shut down. And so they started to try to ramp the reactor back up, but the reactor had already been shutting down. And so a number of things were causing problems, a number of things that are known to happen. Like the reason, okay, so there's a reason when you shut down the reactor that you can't just start it up right away, because there's some elements that exist within the reactor that will absorb neutrons and prevent the chain reaction from taking place. So it creates its own neutron absorbing materials that you have to wait for a few days until they radioactively decay, and then you can start the reactor up again. So Chernobyl was shutting down. It had already gotten past the point where those things existed and you weren't able to sustain the reaction. And so they're like, okay, open it back up. You failed. And so they started opening back up and it didn't work. And so they opened it back up further and it didn't work. And then they opened it back up further. And then there was enough neutrons in the environment to allow the reactor to take off. But now the control rods are out. So the control rods are all the way out. The reactor starts running on its own, like a whole bunch of neutrons come out, takes care of all of the things that were ambient in the environment that make it difficult to start the reactor up, and now it's running away from you. And so then they're like, oh crap, the reactor's running away from us, stick the control rods back in, but the control rods have moderator on the tips and not control substance on the tips. So they started lowering the control rods back down into the reactor, and now they're actually, the first thing that happens is they add more moderator, and that increases the reaction rate, and then the thing blew. And so had this not been there, and had it been control rod all the way down, then it would have immediately started slowing the reactor down. But because they had a moderating substance, the carbon, on the tip, as the control rod was lowered in, it actually facilitated the reactor and made it run away. Okay, let's, what other things? What other questions do we have here? From what I've heard, ship reactors are sealed entirely. Okay, I did that one already. Isn't a reactor in the desert a bad idea, or are those water reservoirs enough? So most of the water is, they do pull up briny water from the water table, I believe, in that. So a desert, the reservoirs are sufficient because obviously it's a functioning power plant. Nuclear reactors do go through water, like you do have to have water to operate them, but I suspect that there are ways for them to keep the water contained within the system so that they don't waste it. Waste it more than necessary. Where are the cooling towers? So the cooling towers for Palo Verde, if it's still up, I don't think it's up anymore. The cooling towers for Palo Verde were the cooling towers for Fukushima, is that what you're asking? They actually use, I think this is their cooling area. So they just run the water down here and they cool the water in these ponds rather than having a cooling tower. Why aren't the containment buildings underground? They don't necessarily have to be underground. They're pretty safe where they are. In fact, you may run into the issue that it may actually be less safe underground, especially if you're like in California. If there's a fault line that runs nearby and you take the containment building and you put a whole bunch of stuff around it, I could imagine if the ground settles, then you're talking about a weight, I'm guessing here, that if you were to bury the containment building, so here's your containment building, it has some, here's your containment building and it's got these walls. Let me zoom back out. Here are the walls, and they have some thickness. If you bury it underground, then you're actually piling an amount of material that is comparable or greater in mass than the building itself. And so if half of this stuff shifts for some reason, like there's an earthquake nearby, then you're talking about having enough material nearby that it might be able to overcome the mechanical properties of the containment building. So it's probably safer to have the containment building exposed to the air in that case. That's my guess. Can Israel bomb the nuclear plants in Iran? Probably. Let's see. How come you can hold a nuclear fuel pellet in your hand when you stack them together and drop them in the water, they start giving off an enormous amount of energy? That's a great question, King's Throne. So you can take a nuclear fuel pellet and hold it in your hand. It's an alpha emitter, and so you might want to wear gloves. Or put a piece of paper on there, because alpha particles get absorbed by almost anything. So they are alpha emitters, so you don't want to swallow it, but wear a glove, you can hold it in your hand, no problem. Because there's no fission going on in when you're holding it in your hand. It's just going through alpha emission. So you have the uranium decaying through alpha emission into its way down to lead. When you put it in the reactor, then any neutrons that come out are being slowed down, or when you put it near a moderator, any neutron that comes out is being slowed down so that it can be more readily absorbed and create another fission event. So here is the nuclear fuel pellet. Mostly alpha emission is coming out. Occasional fission will happen and you'll get a neutron coming out. So alpha particle, alpha particle, alpha particle, neutron. So you get an occasional neutron. This neutron is coming out too fast to create another spontaneous fission nearby. So when you stack these things together and then you lower it down into the water, now the moderator slows the neutron down and makes it so that it's absorbed. The probability of a neutron being absorbed for fission increases the slower the neutron is moving. And so the water slows it down and then allows it to take off. So if you were to take a bunch of fuel pellets and hold it in your hand, and a bunch of fuel pellets and hold it in your other hand and bring them close together, then the water in your hands could act like a moderator and probably not do very much, but you could imagine that's the kind of scenario that you need to have. There are countries working to make autonomous nuclear-powered subs and torpedoes. There's some work being done to mobilize naval reactors for disaster relief scenario. I'm sure that happens all the time. Usually what will happen is that you will send conventional ships, or maybe a nuclear-powered aircraft carrier or something like that, to do the help, and not a submarine. Submarines you want to hide because those are the super duper duper top secret stuff. Why is it designed to fail that way? I'm not sure which way you're talking about the failure. I read that the design of U.S. reactors is different from one used in Daiichi, such that a similar problem could not occur in a U.S. reactor. Well, one thing that's important to keep in mind is that the Daiichi plant was built in, this was 2010, is it late 1960s or early 1970s? And so it's an old reactor. It was built way back in the day. So let's come here and see when it was built. This something, first commissioned in 1971. So it was 40 years old at the time that it had this disaster. And the plant itself isn't the thing that failed, or the plant itself didn't trigger its own failure. It was a tsunami from the largest recorded earthquake in history that caused the backup generators to turn off. And I hadn't planned on going into detail about this because I honestly don't have time to go into detail about it. But ultimately, the main issue that happened here was they planned for the nuclear power plant to operate for sufficient time with its backup resources for new stuff to come in and help mitigate the problem. The issue was a tsunami comes through and ruins all the roads and fills them with houses and debris and cars and boats and stuff like that. And so you can't actually deliver what you need to the power plant on the roads. And so the fact that it became isolated from what would have come in and been able to save it was the real issue. From this picture, you can see these two other nuclear plants. So this area's all been excavated now from that one site. These are the 4 reactors that we can still see, and then these are the 2 that were there before that have been dismantled. Anyway, so 1971, and it failed on March 11th, 2011, 40 years later. because of the largest tsunami in recorded history. So there's that. 3 Mile Island was another set of like really unusual things. Chernobyl was, here's what you get when Comrade tells you to do something and you have a poorly designed system in the first place. Certainly a poorly designed safety system in the first place. The next generation of reactors, which we'll talk about in a future stream, won't have those issues. Okay, so let me make sure that I recap everything that we discussed. We discussed like the basic structure of what a nuclear reactor is going to look like. You're going to have the fuel, you're going to have a moderator, you're going to slow the neutrons down, you're going to have a coolant that ultimately is what drives the turbine. The coolant takes heat from the reactor, drives it through the turbine. And so it cools the reactor by driving the turbine and the power production. Then you're going to have the control rods just to control the reaction itself. It's not an essential thing to have the reactor going, but it is an essential thing to have to control when the reactor goes and when it gets turned off. One of the things I wanted to point out here as a kind of a parting shot on these designs is that often what you'll do is you won't have just one turbine. So here's your reactor core. Here is your loop of steam coming through here, and you'll have a high pressure turbine here. So you have a turbine there, and that takes energy coming out of the steam. Steam comes out at high pressure because you want it to come out at high pressure because that gets you higher temperatures and stuff like that. Comes out at high pressure, and you get some energy coming from here. The kind of turbine that you have for high pressure, the size of the turbine, the size of the blades, the mass that it has, all this kind of stuff, the angle that the blades might have on the turbine, those are all going to be determined by the pressure of the gas that you want to operate. So it's got some optimum pressure where it will operate. So you run it through here. The steam that comes out the other end of this turbine, it hasn't lost all of its energy. There's still energy in there that could be extracted. And so a lot of times you'll have multi-stage turbines. So a high pressure turbine, a medium pressure turbine, and then a low pressure turbine. So these are basically fan blades, and then you drive the steam through the fan blades and they causes it to spin. And so you'll take the steam and you'll run it through a series of turbines to each one providing some energy to drive the generator. And then from here, this is the lowest pressure turbine. The steam has lost most of its energy, and then you condense it down here. So having multi-stage systems like this increases the efficiency of your generator. The same kind of thing happens, as we'll see. We'll talk about other forms of nuclear or of energy generation at a later time. Okay, let me finish up with any questions that we got, and then that will be it for today. Recall more graphite, less liquid water. Oh, so now I should point out with that RMBK, with Chernobyl, the graphite was the moderator. And so by putting the graphite in there, the fact that water was displaced wasn't really the important thing because water was never the moderator to begin with. Water was the coolant that got in there. Any idea why they designed the control rods that way? I have no idea why they did it that way. From last week's lecture on cooling spent rods, why bother cooling said spent rods? Why not bury them in sand somewhere and let them melt down? Well, they wouldn't melt. Well, I guess they would melt if you bury them. So here's the issue. When you take the control or the spent fuel rods out, and this is from, they're going to glow at roughly 1% of the power that they have when they're in the reactor. So if you have a 1 gigawatt power plant, you pull the fuel rod out and it will, 1 gigawatt power plant has all the fuel rods. So if you have as many fuel rods as you have out of the plant that are in the plant when it's operating, then you're talking about 1% of the power. And so now you're talking about 10 megawatts. So 10 megawatts. You could just bury it out in the sand. The problem is if you allow this to melt, then the nuclear fuel, the uranium, and in particular the strontium and cesium, the ones that have short half-lives and are really radioactive, then those can escape, and those can escape into whatever groundwater or anything that's nearby. So you want to keep everything contained, and the way to keep it contained is you can't let the spent nuclear fuel melt through the sides, and so you have to circulate water over it so that you can dissipate that energy without the heat getting to the point where you melt through the side and then allow the molten fuel pellets. So you get up to a temperature where they become molten and where they can leak out into the environment. So you don't want to have that happen. So you cool them for some number of years until the shortest live radio particles are gone, which is going to be like something like 5 years, 5 to 10 years. So a typical power plant will operate for half a century, and so this is a relatively short amount of time. Anyways, there we go. That's what I have for today.